Okay, so we're off to reaction land again, and this time we're going to focus on bromine or chlorine, and that's it. What happens to an alkyne when we add Br2 or Cl2? So let's take a look at another alkyne, kind of what we used before, CH3, CH2, carbon, triple bond, carbon, CH3. And now let's add Br2 in the presence of DCM. Does it look familiar? It should, because we learned this back in Alkynes. Well, first, before we go forward, I want to talk about DCM. Do you remember what that stood for? I hope that you're going to tell me dichloromethane, because that's what that abbreviation stands for. If DCM was not used here, we could also write MECl2. Do you remember what MECl2 stood for? It's the same structure as dichloromethane, it's just the common name with it. This stood for methylene chloride. All right, so dichloromethane, methylene chloride is the same stuff. One's an IUPAC, one's a common name, and we have two abbreviations that go along with it. DCM for dichloromethane, MECl2 for methylene chloride. Any one of these they could write, and if they didn't really want to write one of these or the abbreviation, they could also write CH2Cl2. That's the same exact thing. There's no difference. It just depends on what they want to give you. How bad do they want to try to trick you? That's really what it's all about. Okay, so overall view, we're not going to do mechanism here. Remember, the bromine came in, did a cyclic bromonium ion. The cyclic bromonium ion, bromine hold two carbons at one time, waited for the backup to arrive. The backup arrived, and bromine said, okay, I'm severing ties with one of you carbons, and fink, off it went, and that's where the other bromine went on. This means that no rearrangement takes place. As bottom line, that's what that mechanism means. So we don't have to worry about mechanisms as far as carbocation shifts happening here, which is good news. Wherever that bond is going to be, that's where they're going to end up. All right, so all those rules that we talked about in alkenes holds true. How do we do the product here? All right, well, CH3, CH2, carbon, triple bond, carbon, CH3. So this step is just like all the others. A triple bond will break to a double. Two sides of attachment open up there and there. Don't worry about rearrangement. What are you adding on? Br2. All right, so Br goes on one side and Br goes on the other. Look at there. There's your 1 mole. But what if we wrote excess here? If they wrote 1 mole, that's where you stop. That is not geminal. Why isn't it geminal? Because they're not Gemini twins. The two bromines are not on that carbon, the same carbon. So don't let that trick you up. Now, if it says excess, and most of the time it's assumed excess, by the way, even if they don't write it, I know that sounds a little weird, but you just assume in this field, in this module, that they do want you to go all the way forward. Okay, so excess basically means, folks, it happens again. This double bond is going to break again. Two more sides of attachment open up there and there. And what do we add on? Another Br2. So that means Br will go on one side and Br goes on the other. Look at there. That's all you got to do. That's it. Again, if you know the alkene reactions, you know the alkyne reactions automatically. All right, so how do we name this thing? Longest carbon chain is 5, so this is a pentane. And then on carbon 2, I have a bromo. On 2, I have a bromo. On 3, I have a bromo. On 3, I have a bromo. I've got 4 groups attached there, don't I? So this is a 2, 2, 3, 3 tetra, because there's 4 of them, bromo pentane. 2233 tetrabromopentane. There you go. That's all there is. Again, if you learned the alkene reactions back in the day and realized that Br2 adds on to a double bond, it breaks it, Br goes on each side, The only thing that you have to do is do it again. Take the double bond, break it to a single, add 2 more bromines on it. That's all, folks. Pretty simple, huh? Especially if you did the hard work in the very beginning. So here's an example problem that kind of wraps up the 2 things that we've talked about so far. And the question says, what's the major product for each of the following? And for part A, they give me an alkyne, and they want me to react it with HBr. But notice what they did. They just wrote HBr. They didn't do excess. But I see the word excess in B, and in D, and in E, and in F. So this is a very good sign that, well, they don't want me to assume things. I'm seeing an example problem. They are writing excess in there for a reason, but for A, they did not write excess, and for C, they did not write excess. So that probably is a good sign that they just want me to go 1 step, and that's it. All right. In addition to that, look at A and look at B. All right, so for A, it's a molecule with HBr, and for B, it's the same thing with HBr again. The only difference is that one has excess and the other one does not. So once more, a very good sign that they want me to do 1 step for A and all steps for B. All right, so let's see how these things end up. I'm going to do a carbon with a triple bond and a carbon and a CH3. So HBr, they want me to do this once. So I'm going to take this triple bond and I'm going to change it to a double instead. 2 sides of attachment open up there and there. H will go onto one side, and that side is with the side of the most hydrogens. If I look at the original, carbon to the left has 1. This carbon to the right, it doesn't have any. Hydrogen plays with other hydrogens, so hydrogen's going to go there. That will open up the carbocation that's here. That carbocation right now is Vinlic. However, to the right-hand side, it's primary. It gets no better. So that carbocation, that's where it's going to stay, and that's also where my bromine is going to go. All right, so that's the product for part A. That's the major product right there. For B, they want me to do the same thing, but this time they want me to go through and do excess. All right, so this is not a big deal. I'm going to take the triple bond and I'm going to break it to a double. 2 sides of attachment open up. The first round of HBr gets added on. All right, so H goes here, just as before, and Br goes there. Well, now they said excess, so another round of HBr is going to break a bond. 2 more sides of attachment open up. H plays with other H's, so it has to go there, and that forces the Br to go here. There's your geminal. We've created a geminal dibromide here. Well, if you wanted to clean this left-hand carbon up, you could. So it already had 1 hydrogen. Now it's getting 2 more. So this is actually a CH3 at this point. So I'm just going to erase those. So that way we can put a focus on those 2 bromines right there on that center carbon. All right, so A and B are now finished. Now let's look at C. If I look at C, this is 2-butyne, YNE, and we're adding Br2 and CH2Cl2. Notice again, in all of these others, they're writing excess. In D, they're writing excess. Here, they did not. So it's probably a good sign that they just want me to do this 1 time, and that is it, which is okay. Not a big deal. I mean, we interpret this the same every single time anyway. So let's take a look at the molecule. That's where we start. 1, 2, 3, 4. I'm going to target the triple bond. I'm going to break this to a double. When I do that, 2 sides of attachment open up here and here. The great things about Br2s and methylene chlorides and Cl2s and methylene chlorides, no rearrangement. Wherever those bonds are, that's where they're going to go. So Br goes here and Br goes there. And that's it. That's all that we have to do for that one. Look, are they getting easier? I hope so, because again, you're learning if they are. That's good. Let's take a look at D. All right, so for D, I get this CH, and then I have a triple bond, and then a carbon, and then a CH3. And this time it does say excess, so they want me to go all the way with this one for sure. All right, so triple breaks to a double. 2 sites of attachment open up, here, here. No rearrangement takes place. Wherever they are, that's where they're going to end up being. All right, so I'm adding Br2, so Br on one, Br on the other. Then I need to do it again. It says excess, so I break another bond, and 2 more sites of attachment open up, and Br goes on one, and Br goes on the other. There you go, folks. That's all you got to do. Some people will condense this down in the beginning because that's on the end carbon, and they might do something like a Br2CH, right? If you want to do that, you can. You don't have to, though. I normally do it with hydrogens, but anything else I kind of leave sticking out like white flags just to kind of bring your attention to it. So I'm going to leave it like this. I'm not going to clean that one up anymore at all. All right, so for E. E looks like 4 in a row again, and this time they're doing excess HBr. All right, so not a big deal. We know how to handle this. We'll just think through it, and we'll do one step at a time. Literally, that's what we'll do. So excess HBr, I'm going to break the triple to a double. 2 sites of attachment open up there and there. HBr goes on. If I look at these 2 carbons, both of these carbons are identical. They have no hydrogens on them at all. Hydrogen does not have a preference, so hydrogen will go here to the left, and Br will go here. Well, I need to do one more step. It says excess. So I'll break the double bond to a single. 2 more sites of attachment open up. H plays with other H's. By default, it has to go here, and Br goes there. And that's it, folks. That's all you got to do with that one. Now, the question is, well, what if I did it on the right-hand side and not the left? Well, if that's what you did, you would have ended up with the same thing, because this molecule is a very symmetrical molecule, right? So if you did H here and Br there, H, the next round would go there, and Br would go there, and you're still getting a 2,2-dibromo-butane, just like we have here, 2,2-dibromo-butane. So symmetrical molecules do you a favor, and in here, didn't really matter. Now let's look at F. F is not a symmetrical molecule, is it? So this means that there are some possible choices that I have here that I need to pay attention to. All right, so let me look at F, CH3, carbon, triple bond, carbon, CH2, CH3. So you're going to come in and you're going to break the triple to a double, 2 sites of attachment open up, and you're adding HBr. So you're going to add H to the carbon with the most H's. Well, if I look here and look there, neither one of these have hydrogen on them right now. So I'm just going to write it left-handed first. It's normally what I do because I'm a left-handed person. That's just normally what I do. And then Br gets added on next. All right, well, we need to go further because it says excess. So the double gets broken to a single, and 2 more sites of attachment open up, and H plays with other H's, and Br goes on to the other carbon. So there is one product right there. But I'm going to have to do a big OR. And the reason is because it's not a symmetrical molecule. There was no kind of driving force where these things were going to go. So CH3 carbon, triple bond carbon, CH2 and CH3 again. Well, I'm going to take the triple. I'm going to break it to a double first. 2 sites of attachment open up, and you chose to go left-handed with the H, but someone else could have chose to go right-handed with the H. So that's perfectly okay. So there we go. No rhyme or reason. This has no preference. And then we've got to do it again. So that double bond is going to break to a single, and then hydrogen plays with other hydrogens for sure in that step, and bromine goes on to that position. So in this round, you have created a 3,3-dibromo pentane, all right? And then on the other side, you've created a 2,2-dibromo pentane. And you get both of these, all right? So you want to write both. In A, it was clear cut. H played with other hydrogens. In B, it was clear cut. H played with other hydrogens. In C, didn't really matter. You were putting bromines on both sides anyway, so it would have ended up to be the same thing. In D, doesn't matter. You were adding bromines on both sides. You would have ended up with the same thing. In E, it doesn't matter because it's a symmetrical molecule. So whichever way you put on the H and the Br, if you flipped it, you got the same thing. In F, this is a mixture. This is a mixture of two different ones. We want to clearly show both that show up. All right? Okay, so that's where this video is going to stop. In the next video, we're going to talk about another reaction. And this is a review. It is a review. But there's going to be a new kind of twist on this one. And this is the addition of water. So if you go back and take a look at alkene reactions, you know that when we added water, we pretty much added H and OH onto the molecule. We took the HOH for water, split it like we've always been doing. Hydrogen goes on one side and OH goes onto the other. That was the shorthanded way of looking at this mechanism, even though that's not really what happens. It's the shorthanded way of looking at the reaction. So, how does this change in the world of alkynes? Does it? The answer is yes, it does. It slightly changes, and it's something that we have to watch out for. So that's what we'll talk about next when we come back.